Lesson 6. Motors. Motors for FPV drones are a key component that affects the drone's performance, maneuverability, efficiency, and overall behavior during flight. The choice of the right motors depends on the type of drone, flying style, and personal preferences of the pilot. Choosing the wrong motor can lead to a loss of drone efficiency, insufficient thrust even for takeoff, and incompatibility with the ESC or battery. This, in turn, can result in wasted money and a loss of enthusiasm. Before choosing a motor, it is important to pay attention to the following characteristics. Determine the type and size of the FPV drone and the manner of control. Consider whether you will be flying far or fast. This will affect the frame shape and the size of the motors, along with their energy efficiency and thrust characteristics. Choose the type of motor, brushed or brushless. Select the propeller size relative to the frame size. Consider the motor's stator size and weight. Lighter motors reduce the overall weight of the drone, which can improve maneuverability and flight time. The weight of the drone itself. The current consumption of the motors will determine the selection of the appropriate ESC and battery. kV rating. This indicates the number of revolutions the motor makes per minute per volt. A high kV rating means higher speed but lower thrust, and vice versa. Calculate the required thrust and how much weight the drone can lift. The number of poles and magnets on the motor for effective drone operation. The mounting sizes of the motor and frame. For FPV drones, the following types of motors are used: brushed and brushless. Brushed motors are rarely used for FPV drones. They have a simpler design, making them cheaper to manufacture and repair. Brushed motors are easy to control with simple electronic speed controllers, ESC, which reduces the overall cost of the system. Their main disadvantage is the faster wear of the brushes, which requires regular maintenance and replacement. They are less efficient compared to brushless motors, which can affect flight time and drone performance. Brushed motors are often used in miniature drones or toy models where high performance is not required. Brushless motors. Brushless motors are the most common for FPV drones, especially among professional models. They have a more complex design and operating principle, which ensures high efficiency and reliability. Brushless motors operate through the interaction of the magnetic field created by the stator windings and permanent magnets on the rotor. The electronic speed controller, ESC, manages the current supplied to the windings, changing its direction to create rotational motion of the rotor. Brushless motors have higher efficiency compared to brushed motors, allowing the drone to fly longer on a single battery charge. The absence of brushes reduces mechanical wear and the need for maintenance, increasing the reliability and longevity of the motor. They are capable of operating at high RPMs, making them ideal for FPV drones that require high speed and precision. A brushless motor consists of the following components. Stator, the fixed part of the motor that does not rotate and is mounted with screws to the frame. Its housing is typically made of aluminum or another lightweight metal. It provides mechanical support and protection for other stator components. Bearings are pressed into it for the rotation of the rotor shaft. The stator core is made up of thin sheets of electrical steel that are joined together. This reduces eddy current losses and increases the efficiency of the motor. The stator has copper wires coated with lacquer, which are divided into 3 phases wound around the stator core. Next, the motor consists of a rotor, which is the moving part of the electric motor that rotates under the influence of the magnetic field. Inside the rotor, magnets are glued in place using epoxy resin and are arranged in a circle. These magnets interact with the magnetic field of the stator, causing the rotor to spin. The rotor housing serves as a protective cover for the magnets and windings. Typically, rotors are made from lightweight metals such as aluminum. Some rotor models are designed like miniature fans to direct airflow onto the stator windings for additional cooling during motor operation. The rotor has a shaft at its center that rotates on bearings mounted on the stator and transmits torque to the propellers. Through the rotation of the rotor, electrical energy is converted into mechanical energy, allowing the motor to perform its work. When a motor burns out, it is typically the winding on the stator that fails. On the outer part of the rotor, you can see an abbreviation in the form of words and numbers indicating the manufacturer of the motor, the size of the stator, and the number of revolutions of the rotor per minute per volt. For example, if we take a motor labeled Xing E Pro, this is the brand name of the motor. A 4-digit number, such as 2207, means the following. The first 2 digits indicate the diameter of the stator, which is 22 millimeters, and the last 2 digits, 07, indicate its height. It is important not to confuse this with the rotor. These dimensions refer specifically to the stator of the motor inside. The parameters are specified in millimeters. Increasing the width or height of the stator increases the volume of the stator, the size of the permanent magnets, and the electromagnetic coils of the stator. As a result, the overall torque of the motor increases, allowing it to spin the rotor faster and produce greater thrust by consuming more current. However, the downside of a larger stator is that it is heavier, which can lead to slower responsiveness to the pilot's commands. Wider motors have greater inertia when rotating, as the mass of the motor is further from the axis of rotation, requiring more energy to change the RPM. Such motors are usually less sensitive than narrower and taller motors, even if they have the same stator volume and generate the same torque. Wider and shorter motors also have smaller magnets on the rotor, which can reduce the power of the motor. However, wider motors provide better cooling due to the larger surface area on the top and bottom. Temperature is critical for motor operation. When the motor heats up, its ability to generate magnetic flux decreases, affecting efficiency and torque production. Essentially, the width and height of the motor's stator represent a balance between responsiveness and cooling. The decision depends on your flying style. For example, for slow sinew hoops with a heavy GoPro, you may need motors with a wide stator for better cooling. For racing or freestyle drones, it is better to use taller stators. Larger stators are not a panacea. For example, 2,207 motors can work with typical 5-inch propellers, but using much heavier 2,506 motors may not provide noticeable advantages, as they will generate the same thrust using the same propellers or even offer worse responsiveness compared to 2,207 due to their increased weight. High-torque motors provide quick changes in RPM and shorter response times, leading to reduced vibrations of the propeller. The torque of the motor is determined by several factors, including the size of the stator, the material it is made from, the type of magnets, the quality of the copper winding, the design of the motor, air gaps, and the number of poles. The size of the stator can be calculated using the formula for the volume of a cylinder. This formula is as follows. V, the volume of the cylinder. Pi, the mathematical constant, approximately equal to 3.14. R, the radius of the base of the cylinder. H, the height of the cylinder. Let's take our motor with a stator size of 2,207 as an example. Using this formula, we obtained a stator volume of 2,659. The larger the volume of the stator, the greater the torque that this motor can generate. In comparison, the volume of a 2306 motor will be 2492, meaning the 2207 will have greater torque due to its larger stator volume. When choosing a motor, compare the stator volume and its weight. Lighter motors with the same stator volume will operate more efficiently. Motor sizes vary depending on the type of drone and the size of the frame. 1103, 1104, 1105 for micro drones. 1404, 1407, 1507 for lightweight and medium drones. 2204, 2205, 2206, 2306, the most common for 5-inch FPV drones. 2507, 2806 for large or heavy drones. Manufacturers of frames often specify the recommended motor sizes for each of their models in the description. Lightweight drones do not require the pilot to apply high throttle to stay in the air. In this case, the torque requirements for the motor are low, allowing for the use of more compact and lightweight motors, which overall reduces the weight of the drone. A less powerful motor, with lower torque, is preferable in one scenario, when smoothness is more important than the drone's responsiveness. High-torque motors can change RPMs so quickly that they may feel jerky and less smooth. They can also generate more voltage spikes and electrical noise in the power system, potentially affecting the performance of the gyroscope and overall flight performance if noise filtering is not optimal, leading to drone oscillations. The number with the kV prefix, in our case 1800 kV, indicates the number of revolutions per minute, RPM, of the motor for each volt applied to the motor without a propeller, meaning under no load. For example, if 1 volt is applied to this motor, it will have 1800 RPM in 1 minute. If 20 volt is applied, it will reach 36,000 RPM. If we use a fully charged 6S battery at 25.2 volt, we will have 45,360 RPM of the rotor per minute without load. During the operation of the drone, its battery discharges, and consequently, its kV value will decrease. For example, a nearly discharged 6S battery will have a voltage of 21.6 volt. The difference is 3.6 volt, which means the motor's RPM will decrease from 45,360 to 38,880 RPM, a reduction of 6,480 RPM or 15%. Therefore, with each passing second, the drone will lose its RPM due to the decreasing voltage of the battery. When a propeller is installed on the motor, the RPM sharply decreases due to air resistance. If you have batteries with different S ratings, such as 6S and 4S, your drone will fly faster and be more maneuverable on 6S, but it will not fly as long as on 4S, where the drone will be less maneuverable and slower compared to 6S, but will fly longer due to the lower voltage per volt. Motors with a higher kV will attempt to spin the propeller faster, generating greater thrust and power, while consuming more current. Larger propellers are usually paired with low kV motors, while smaller and lighter propellers work better with high kV motors. If a high kV motor is paired with an excessively large propeller, the motor will try to spin quickly, as it would with a smaller propeller with less resistance, requiring more torque. This increased demand for torque will lead to higher current consumption and heat generation. Overheating can cause the motor to burn out, as the insulation on the stator winding can melt and cause a short circuit inside the motor. The kV of a motor is determined by the number of turns of copper wire in the stator. In general, a larger number of winding turns reduces the motor's kV, while a smaller number of turns increases it. The magnetic strength of the magnets can also affect the kV value, as stronger magnets increase the kV. The kV of the motor does not directly affect the torque but influences the torque constant. The torque constant of the motor determines how much current is needed to generate a specific torque. Factors such as magnet strength, air gap, and winding resistance have a significantly greater impact on torque generation. Motors with higher kV have a higher torque constant, meaning they require more current to produce the same torque compared to a motor with lower kV. To generate the same torque, a higher kV motor needs more current, leading to additional losses in the ESC, battery, and wires. Additionally, more heat accumulates in the motor due to the higher current, resulting in a lower magnetic flux. Overall, a motor with a higher kV is less energy efficient if flying at the same speed as a motor with a lower kV. Therefore, it is important not to overdo it with the kV value. This is especially crucial when building drones for long-distance operations, where energy efficiency and flight time are prioritized. Large drones require more powerful motors with a low kV value. Motors mounted on the arms at the four corners of the frame have a significant impact on the feel of the drone. Heavier motors increase the moment of inertia, requiring more torque, not just thrust, for the motors to change the drone's position. In real flight scenarios, when your drone performs flips and rolls, it takes time to gain angular acceleration, reach the desired position, and then stop. Heavier motors require more time to achieve the necessary angular speed and to decelerate, which makes the drone feel less responsive. This is especially important if your flying style involves quick direction changes, such as in freestyle or racing. For those primarily focused on cruising in a straight line, such as in cinematic setups, the weight of the motor may not be as critical. Temperature plays a crucial role in the performance and longevity of brushless motors. The magnets used in these motors exhibit a weaker magnetic field at higher temperatures, which can lead to faster demagnetization and affect the lifespan of the motor. Overloading the motors or excessive use of full throttle can cause your motors to overheat. This, in turn, can degrade the performance of the motor and its magnets over time. As a result, motor designs that have better cooling often correlate with a longer lifespan. Vibration generated by the motors can lead to several undesirable effects on the operation of your drone. A motor with poor balance or low assembly quality can generate vibrations that may affect your PID controller. As the frequency of vibrations changes at different throttle levels, tuning your drone can become increasingly complex. Additionally, a vibrating motor will produce more electrical noise than a smoothly operating motor. This electrical noise can interfere with your gyroscopic sensor, further degrading flight performance, and may even affect video quality if your VTX system is powered directly from the drone's battery. The motor shaft is an integral part of a brushless motor, as it is responsible for securely attaching the propeller. Most brushless motors designed for propellers ranging from 3" to 7 have a diameter of 5 mm. This is referred to as the shaft diameter. If, in this case, it is 5 mm, it means that the propeller also needs to have a hole size of 5 mm. All the characteristics of the motors mentioned earlier affect their thrust. This parameter is very important as it will determine the speed, maneuverability of your drone, the ability of the FPV drone to lift itself, as well as any additional weight in the form of a camera, larger battery, etc. To calculate the minimum thrust required for the combination of a motor and propeller, you will need an approximate total weight of your drone. The general rule is that the maximum thrust produced by all motors should be at least twice the total weight of the FPV drone. Insufficient thrust can lead to delayed response to control inputs and difficulties in takeoff. In extreme cases, the motors may burn out. The thrust of the drone is calculated as follows. Knowing the specifications of the motor, namely its brand, stator size, and kV rating, you can look up the manufacturer's test chart for that motor. This table contains information about the amount of thrust that our motor will produce at a certain throttle setting using a specific propeller. Depending on your flying style, smooth and stable or pushing to maximum throttle, you look at the percentage value of the throttle, the gas at which you plan to fly for most of your flight, and accordingly, the amount of thrust the motor will produce at these parameters. This way, we obtain the thrust per motor. For example, in this table, I select this propeller for the calculation and look at 100% throttle. This motor produces 1,700 grams of thrust. To calculate the total thrust, we multiply the thrust of one motor by 4. This results in 6,800 grams of total thrust from the motors. The drone, when equipped with a battery, weighs 1 kilogram. This means we have a thrust-to-weight ratio of 7:1, where 7 is the thrust of the motors and 1 is the weight of the drone. For racing drones, the thrust-to-weight ratio should be significantly higher than in the example above. Ratios of 10:1 or even 14:1 are not uncommon. For freestyle, a ratio of at least 5:1 is recommended. The key is to have no less than 2:1. A higher thrust-to-weight ratio gives the drone greater maneuverability and acceleration but can make it more challenging to control, especially for beginners. Even the slightest touch of the throttle can launch the drone into orbit like a rocket. Piloting skills and experience play a significant role in managing this power. Even if you plan to fly in a calm manner for aerial photography, aim for a thrust-to-weight ratio above 4:1. This provides better control of the drone, preventing it from trying to go out of control and leaving room for additional payload. When choosing a motor, you should check its mounting holes for attachment to the FPV drone frame. Common motor mounting patterns, the distance between the holes, are 16 by 16 mm and 19 by 19 mm. It is important that the mounting holes for the motor match the mounting holes on the frame. When mounting the motor to the frame, you need to carefully tighten the screws to avoid damaging the stator windings. First, Measure the distance from the edge of the frame to a safe distance from the stator windings before tightening the screws. Otherwise, the screw may damage the copper wire and burn out the motor. You need to select the appropriate ESC for the motors. It should meet the current consumption needs of the motors. The specifications of the motors include nominal and peak current consumption. The nominal current is considered to be the continuous current supplied to the motors during the entire flight at a specific throttle percentage. For example, if you do not exceed 50% throttle, your motors will consume no more than 10 amps throughout the flight. By the way, the maximum current specified in the motor specifications, which is stated at 100% throttle, is also considered the nominal current. However, if you fly at a constant 100% throttle for more than 1 minute, your motors will likely overheat and burn out. Additionally, the maximum current specified in the specifications does not account for the current consumption of the motor with the propeller installed. The peak current is considered to be the sudden increase in current consumption by the motor with the propeller installed during a sharp maneuver. This leads to current consumption that exceeds the maximum current stated at 100% throttle. Therefore, it is very important that your ESC can deliver at least 10 amps more than the maximum current consumption of the motor. When reviewing motors for your FPV drone, you may come across specifications such as 12N14P. Here's what these numbers mean. The number before the letter N indicates the number of electromagnets, poles, in the stator, while the number before P indicates the number of permanent magnets in the rotor. More poles equals smoother operation of the motor. Fewer poles equals increased power. Since FPV drone motors are typically three-phase, the pole configuration must be a multiple of 3, 9, 12, 15, 18, etc. This is due to the presence of 3 wires leading to the motor. This characteristic is not a critical factor when choosing motors, especially for FPV drones. However, you should pay attention to the number of poles, as you will need to enter this number in beta flight when enabling the RPM filter. If you cannot find this number, you can simply count how many magnets are in the rotor. In the construction of the motor base, there is a more traditional approach with a closed bottom and a more modern style with an open bottom. Both of these designs have their pros and cons. The closed bottom design means a sturdier base. However, an open bottom tends to be lighter due to the removal of excess material, resulting in a weight savings of approximately 2 grams. Motors with a closed bottom are less likely to allow dirt to enter the rotor, whereas dirt is easier to clean from an open bottom. With an open bottom, you can clearly see how far the screws are drawn in when mounting them to the frame, and you have a lower chance of damaging the stator winding with the screws. The durability of the motor depends on the metal used for the rotor and the motor base. There are 2 common types of aluminum alloys used in FPV motors, 7075 and 6082. The number indicates different series of aluminum alloy grades and their chemical composition. 6082 has greater plasticity, while 7075 is stiffer and better withstands impacts, making it the most common in modern motors and considered more impact resistant. When it comes to securing the motor shaft, one of 2 methods is used: C-clamps or screws. Each method has its own set of advantages and disadvantages. Screws are easier to unscrew, making motor maintenance simpler than with C-clamps. However, screws have a higher risk of being over-tightened, which can lock the shaft and make it difficult for the motor to rotate, or even cause it to seize to the shaft, making servicing impossible. C-clamps can come loose during flight, which may result in the motor rotor flying off and causing a crash. They often break and get lost during disassembly, but they are lighter compared to screws. Additionally, not everyone has the convenient tools on hand to remove or install them. Using curved magnets instead of straight ones allows the magnets to be positioned closer to the stator, creating a smaller and more stable air gap. This, in turn, provides better motor performance. The magnets used in brushless motors are classified according to their magnetic field strength, such as N50, N52, N54, with larger numbers indicating a stronger magnetic field. For example, a motor with N52 magnets will perform better than one with N50 magnets. A stronger magnetic field theoretically allows the motor to generate electrical energy more efficiently, resulting in higher torque and faster response times. However, a motor with a stronger magnetic field is not always better, as it may indicate a less uniform magnetic field, which can lead to less smooth motor operation. This can be felt when manually rotating the motor, indicating how strong its magnets are. Stronger magnets make the motor feel more abrupt. It is also important to note that magnets can lose their magnetic strength at high temperatures, which can affect the motor's performance. To address this issue, motor manufacturers often use N52H magnets, which are designed to withstand high temperatures. Some motors even use N52SH magnets, which are believed to be capable of withstanding even higher temperatures. Be sure to pay attention to the voltage at which the motor operates as specified in its description. This will determine the number of revolutions per volt. If you connect a battery with a higher voltage than indicated in its specifications, the motor will burn out immediately. Cleaning motors for FPV drones is an important part of maintenance to ensure their longevity and efficiency. Motors that have fallen into sand or mud require thorough cleaning to prevent them from seizing, which can lead to the burning of the stator windings. For this, compressed air, a cloth, or a toothbrush can be useful. In field conditions, pilots often blow out the motor and rinse it with plain water, then blow it out again. If the situation is particularly severe, they completely disassemble the motor and perform cleaning procedures. Those who frequently fly at high throttle values will need to service the motor bearings more often due to the increased load on them. This can be checked by sound. Take each motor and manually rotate them in turn. If you hear a bearing starting to hum, it must be replaced to prevent it from seizing during flight or creating excess vibrations. If the rotor on the motor is bent or visually damaged, it can also create excess vibrations on the frame or cause the motor to overheat. If the motor is forcibly stopped during operation, it will burn out. For this reason, you should not apply throttle when the drone is stuck against an obstacle.